Hi. So before we start, so let's some administrative thing first. So the homework for homework 3 is due on Friday midnight. So make sure that you are done with that at the end by the end of Friday. The second announcement I want to make is about the exam venue. So we eventually can book the day, book the time, book the venue. The time has been same as we have announced. The venue is YIALT3. So it will be a 1 hour test and then open book. So that would be the administrative things. I mean, I will give you further details. Is needed further instruction of the test when the days comes close. So what's the goal today? The goal today is to finish this topic estimation and have some preview on hypothesis testing. So I guess it'd be good to I guess it's good to review what we're going to do. Okay. So what we're going to do is trying to maybe a whiteboard, right? So what we've been doing, right, so far is the following, right? So we have a population, right, is the object that we want to study, right? Say if your business application, you want to look at, say, the potential customers in the city or in the country, right? And maybe each cross is representing if a customer, maybe people there, right? Potential customer is represented by cross. Okay, so there are many customers, and usually you would care about how much income they have, right? Because when you sell them the product, right, you care about the income, right? The only thing you may care is about income or age or many things, right? Income or age, right? Or wealth, so on and so forth. You care many things, right? And you'd be good. The nicest thing, right? You can imagine you have is that you have the distribution of this, right? The distribution, right? You can draw a histogram. You can do whatever you like, right? Basically, you have everything there. You'll be good, right? Every data is the dream thing you want to have, but usually you really can't have luxury of that. So usually what you have look at is rather the summary statistics, right? That's something you can hopefully can get the information, right? Summary statistics, right? So you would be hoping to get information on mean, right? The meal and sigma square, variance, and many other things as well, right? And these are all the what we call the parameter of the model, right? The parameter, population parameter. Okay? There is something we want to know. There's a parameter. Okay. And as I said, if we're able to observe every single elements in the population, then we can actually get this number, right? But the point is like getting all the information will be very costly, right? Say if you want to get the information, you need to really have to ask everyone there, right? That is not practical or not cost effective or time effective to do so, right? The thing is like you would instead, what you're going to do is instead, right? You would be doing a sample, right? You're going to take this out, right? And what are you doing is in this sample, right? We hope this sample, okay, which is a small picture, right? A small picture here. And we want this sample, okay, to be representative, right? We want a representative sample. representative. Okay. So why? Because you want this sample, okay, to be able to reflect what is happening in the whole big picture, right? So basically, is the reason why I want this is I want the small picture, right? The small picture, which is a sample, right, can tell us what happened in the big picture, right, which is population. So basically, this is the idea, and how to make this representative, right, is through random sample. Okay. Random sample, right? And in our class, we focus on a particular case we call simple random sample. Okay. And in the sense that everything you have the sample is randomly chosen so that this is a representative one, right? So, and what is the goal here, right? Because we want to get what is the parameter, right? So that is what we want is to try to use this to guess mu and to guess sigma, right? And how can we guess that, right? And we learned this estimation, right? Is okay, the estimation is through, to estimate this, we have x bar, right? To estimate this, we have s squared, okay? And you want to ask why they're good, right? Why they're good. The question, why these are the good one, right? Because they have good property, right? The most important property we cover is called unbiased. The unbiased estimator, right? If you remember what's unbiased, it means that if you have, hypothetically, you repeat this process many times, each sample, you have a sample mean, and average of those sample mean you actually equal to mu. Okay, you're supposed to repeat this process, but of course you just only do once, right? And maybe you do several times more, but you never do big enough to enable you to actually discover mu. But I mean, at least this process, we have hope that it's going to be an unbiased one. Okay, that is the one goal. This is how to estimate, and particularly these are actually called, this we covered last time. This is called point estimator. Okay. So why this is a point estimator is because of these only give you a number, right? Just give you a number instead of more than a number, right? Is point estimator. And the alternative actually we will learn today is called the interval estimator. Right, the interval estimator. Okay. Interval estimator, what's the goal of that is instead of giving you a point, we'll give a range, right? It gives us some precision idea. It's like instead of saying, the stock Hansen index is going to be a certain number, you give you a range of number, right? That's often they give you, right? So the highest can be this, the lowest can be this, and anything in between is like uniform distribution, right? That's usually people assume, right? So that is what interval estimator, right? And today we cover how to construct this interval estimator, right? How to construct this. The idea is very simple, okay? And we only focus on the case of x bar, okay? Or estimate on mu. How do we do that? Basically, what we'll do will be, we will have interval where we will have interval, right? There's no interval with x bar plus m and x bar minus m. And that is, we will extend from x bar, which is our unbiased estimate on mu, go to the left-hand side and right-hand side symmetrically. Okay. And we will tell you what's the mu, but that's the goal. Okay. And graphically, it means the following. if you recall, if we assume normality assumption, and what we have is X bar will have a bell curve over the mu, right? The bell curve. Okay. So what is interval estimator we are talking about is X bar can be any number here, right? Following the bell curve, right? So interval estimator means the following, in the following sense. I have this is maybe the sample mean I calculate, and I will go left by M, okay, and go right by M, okay, and the interval estimator is going to say if I do this process, I go left by M, go right by M, okay, there will be a high probability that the X bar, this interval will include the mean. Okay, let me repeat the statement. I'm saying is before I do this, right? Before I do the sampling, I have the procedure, I specify a procedure, which is I will calculate sample mean, which is adding all the data divided by n, the sample mean, right? And I will do an M, we'll tell you what's an M, right? And look that the M is independent of your sample. Okay, M is pre-specified, is not, in this case, not affected, okay, by the sample. Right. And I will go left by M and go right by M, right? And then this interval, okay, will have a high probability that will include mu. Okay, I'll be more formal later, but this is the goal of what we're doing. And after the break, we'll talk about the case of kind of reversing this process. Is called what we call later. We'll talk about after the break. We'll talk about what we call here we'll call sample size. Okay. So as you will see later, this M will be depend on the sample size you got. Okay, and that means if I want a certain M, okay, that means I want the precision, right? M is how precise your estimate you are, right? So then if I want to fix my M, so I need to change my sample size, right? Because that is, I would have to decide my sample size and I do the calculation, right? I will start with the sample size and I do the calculation. But now I reverse it. Suppose I want to achieve some M, okay? So what should be my sample size? Okay, so please go back one step backward. At the beginning, just like what some of you might be doing a survey for your projects, right? And the question is how many samples you got, right? So that would be the question we're asking. Okay. So I guess this is good. I mean, it's a good overview. I think I hope it's clear what we are going to do. But let's go back to the what we're going to cover. Okay, estimation. Okay, quickly. As I said, parameter. The things usually the summary statistics, right? About the population, right? Sample mean, population mean or population variance. Although we don't cover in this class, you also sometimes interested in kurtosis and skewness and other things that you may like to understand. Okay. And estimator in general is a function of random sample, right? Just like you give me some observation, you just by estimator is a way to estimate, right? The sample mean is a way to estimate the population mean, right? Sample variance is the way to estimate population variance. And estimate is a value of the estimator. So it's a number, okay? So do note that estimator is a random variable, right? Because it's a function of random variable. And estimate is a number, okay? So there's no uncertainty related to the estimate, okay? That will be a tricky part. Later we'll talk about interval estimate, the confidence interval. That's why we don't talk about probability. The reason is once it becomes estimate, we cannot say anything about probability anymore. Okay, I will talk about this in further detail soon. Okay, so there are two types of estimator, as I have said, right? There's a point estimator or interval estimator, right? By point estimator, it means that it just gives you a number, right? Interval estimator is give you an interval, right? So just to remind you, a figurative representation of point estimator, right? It's like the following, right? Suppose, okay, you are the protagonist, right, of a film, right? And there may be a ghost, okay? There, right? So you try to shoot the ghost, right? And if you have a pistol, okay, you just hit, then that will point estimator, right? So that is a point estimator, okay? And what is a interval estimator, right? It's like this. Okay, you will be having a rocket launcher, and then you have to hit, then you will bomb. Okay, bomb. Then this will be a interval estimator, right? Instead of hitting a point, you just hit a large area, right? It's like go nuclear, yeah? Boom, right? Or throwing a grenade, okay? It's not going to be hitting one point, but a bunch of points, okay? And this giving you a bomb or a nuclear actually also tells you how precise or how accurate your estimate is, right? Because instead of telling a point, I tell a bunch of points, and it's just likely that things fall within. So that means that you're actually giving more information, right? Because point estimator, usually what you do is unbiased estimator. It will just mean that it's equally likely to be above or below, right? Doesn't tell you the kind of distribution, right? Of course, we cannot talk about distribution, but we'll say it's very likely, we believe, okay? That's not probably what we have confidence, right? We believe that it will be within there, okay? So that would be the idea, okay? So instead of it tell us how good is your data, right? Because if your data actually say you want to collect average income, right? If your data tend to be very concentrated on certain value, right? And that means the interval estimator also very narrow, right? So it's very precise, right? Even though you use interval estimator, right? It's different from the real world, right? You want the bump as large as possible, right? But here actually we want the bump as little as possible because it tells us it's very precise. Is that clear? Okay. I hope that would be I like this graph. Maybe I'll take a picture. I can show to my son, this is what I'm teaching, because they keep asking me what I'm teaching in school. But I think they understand this one. Other than they can understand because they only one is primary school, one is like kindergarten. So I think they understand this graph. Okay. So I mean, this is also a point estimator and interval estimator also up here in TV, right? And especially these days we have a huge fluctuation in financial market, right? The financial analysts in TV will often give you, usually the news anchor would ask them, there will be, two estimates they will get, right? They will say, what's the target price, right? They'll give him one number, right? What's what's the target of say Hansen index today, right? They usually give, okay, this is number X, right? And then they, or probably they would be asked what would be the range, right? They would say the highest is this, the lowest is this, right? Or in more terminology, we have say they call the resistance, right? And this or the lower bound, right? Or the upper bound, right? And will be on certain number, right? There's maximum, minimum. Okay. In that case, implicitly they talk about interval estimate. They talk about the biggest and lowest, and actually when they meant that, they actually talk about interval estimate. Right. So I hope that's clear what we are talking. Okay. So let's go to point estimator. Okay, point estimator. So I guess this is we know very well. It's unbiased, consistency, efficiency. So I guess it's good to just look at the definition, and the graph will be sufficient because we covered that last time. So unbiasedness means that if you do many times, okay, which we don't remember, just do once. But suppose hypothetically you do many times, average of them actually get what we want. Okay. So in this example, is suppose the estimator, there's some way to estimate theta. Okay, maybe you use a type of gun or type of weapon, right, to hit the bullseye, right? And this bar or this weapon actually can end up either this, or this, maybe more. But the goal, the key here is like potentially it end up in here, right? But there's no way near theta. Okay, but on average, it's hitting target, so it's unbiased. Okay, it doesn't mean that it will ever hit the center, but it just means that average will hit the center. Okay, of course you will say this is obviously have no use, right? I mean, you would say, but this is the kind of minimum requirement, right? If it doesn't satisfy, then there's no hope of recovering it, right? Because the idea of light is science, right? We wanted to discover one fact. One scientist told to do one experiment, the other scientist do another experiment, the other scientist do another experiment. Okay, and if you average of those results from those experiments, you get what we want, then at least there's some hope to discover the truth, right? So that means the unbiasedness is, although weak, but is at least is something that we should expect to have, right? If that's not the case, then likely there's no hope to discover anything. Okay, so that is very weak. Okay, so that's why we strengthen this idea while talking about efficiency, right? Efficiency means that compared to unbiased estimator, okay, look at unbiased. If one estimator actually is closer to what we want to measure, or closer to target, that's more efficient, right? Graphically, it means it is say A, right, can realize in this free value is also centered at theta, B also centered at theta, but A is much closer than B, right? So that is the idea of efficiency. It's like it's more accurate, right? It's just like on average, both of them are hitting the target, but A is much more closer to the target. Okay, that is efficiency. Okay, and this is right. It's like how do you pick when they are both efficient, right? Because unbiased is a weak concept, so that's why we need to tell us how to choose among those unbiased estimators. Okay. Lastly, this is a little bit more trickier concept. Okay, but this is also very natural. Is remember unbiasedness saying that if we keep doing sampling out of many samples, the average of the estimator estimate is actually going to be what we want. Okay, so this one is then going to another dimension. Instead of doing many samples, we talk about a single sample, but the sample size expands to as big as we want. So we just keep collecting data, okay, collect data and calculate just once, and the calculation, the estimate actually get into what we want. Okay, and the graphics you can see is like this one. So one is like sample size of one, right? Here, these three actually you can see the center is something like here. Okay. I think something like here, right? It's not unbiased. It's a biased one. Okay, It's not centering there. Okay. And the second one, maybe look at this red. Okay. Okay. I think it's somewhere here. I feel it's somewhere here. And look at 3. Okay. Maybe somewhere here. Okay. So when you increase the sample size, okay, you notice that they're getting closer and closer to theta, right? Even though each time is different from theta, okay? And you can imagine, I don't draw it, but you can see when the sample size increase, okay? At the end, it will shrink the closer and closer to theta. And if at the end, it becomes the point theta, then it's called consistent, right? So that means that if we able to have a lot of money, we collect a very big sample, we get what we want, okay? Then it's consistent, okay? And this is a very useful or very important as well, right? Because if it's not consistent, right? And why do we spend money on doing large sample, right? Just do small sample when we're done, right? I mean, we do a lot of big sample. Is a big sample actually will be useful, right? I mean, that would be the key point of this. And why we introduce 3 of them, right? Because they will be very useful, right? Because they explain, first is, we don't go to detail, but sample mean is satisfy the 3 property, right? It's a consistent, it's unbiased, it's efficient. Efficient, you have to define what is, but technically it's efficient among those weighted mean, okay? But I'm not going to detail on this, but at least the carrying message is efficient under some condition, okay? So that's something you need to only to know. It's efficient among those things, because it's difficult to prove further for the math we need, okay? We have. So the next one is sample variance, okay? So what we are saying here is, what to remember here is why we have -1, okay? Instead of n, okay? So my first answer to you, there are several layers to this answer, increasing complexity. The first one, we will invoke the idea of called unbiasedness, right? So this is actually this guy, okay? So this is our first defense, is because this is unbiased, okay? So which means that if you use this, okay, you will not overestimate, you know, underestimate on average, okay? Or on average doing this, you get what we want. Is that clear? The first line of defense for this one, okay? The second thing probably you want to understand is why you have n-1, right? Why n-1? Why? Okay, why n-1? There are several layers of you can understand, but the main thing is you have to estimate x bar instead of using mu. Okay. If you are given mu, or we know mu, okay, and there's no need to do n-1. Actually, you can see this from the proof. Okay? Although none of you will, I mean, maybe a very few of you read the proof, but that's the main thing. You can look at the proof. You check out because of x bar. That is the reason why we need to have n-1 for 1 to hold, right? Because this is behind the reason we have unbiasedness. Okay. And if you want to go further with document proof, that is what we call the idea in statistics. That is related to some idea is what we call degree of freedom. Okay. Okay. What does that mean in general in statistics? And actually we will encounter later in the course, or also in other contexts, is when we trying to estimate variance or whatever other thing as well, is once we have estimate, our estimate will depend on, if our estimate depend on things that we have to estimate. So what do we mean by that is, we estimate this one, we need to first estimate x bar, all right? So in order to estimate something, we need to do one thing else. Then the degree of freedom will subtract from 1, okay? If you estimate two things, you subtract from two. Okay, so this general concept. Okay, so why we need to estimate one thing and we do the calculation would have to reduce the degree of freedom. So let me explain in this context. So the idea is the following, very quickly. I mean, if you don't get it, it's okay, because one day you'll get it as well. Because I also mentioned when I was a student, it took me a long while to understand this. I mean, it's not required for our class, but if you read a book, they will explain it this way. Some of the book will say, the main reason is what you're doing in variance. Variance is looking at the distance between this and this, right? And the square, you do it for every single one, right? And the n of them, right? So that's why you divide by n, right? So that is the thing you do for the mu, right? Okay, you just sum up all of them and divide by n, right? Square distance and over by n, right? Why, when you have x bar, you will divide by n minus 1 instead? Okay, the reason is because this is a number that calculates from your data. Okay, you calculate this, right? You calculate this to get x bar. Okay, that means that actually not all the number you can change, right? Because suppose we know the x bar already, okay, which you calculate, right? And you can only free to change the first n minus 1 number, okay? You can change all this number up to here because x bar, you know it, this guy already fixed, okay? So this is why the last variation, the last measurement, actually is not there. Because once you fix you're free to change the first n minus 1, whatever number you can put, right? But the last one will be fixed by this relation, right? So because to estimate this n up, okay, you only have n minus 1 variation to measure. So that is the idea of degree of freedom. As I said, you don't need to see it but later if you do statistics, you will see the standard rule is if you estimate one parameter, then when you calculate variance, you have to divide by minus 1. If you estimate 2, you minus 2. Estimate 3 variable, then you minus 3. Okay. Of course, it's not clear why you estimate more than 1 or 2 or 3, but later you will see when you do regression or ANOVA, you will see at the very last of our course, you will see actually we minus many of them when you calculate the variance. Okay, it will be more clear later, but of course, if you don't understand this, because this is just a mathematical proof, right? So if you really don't like the intuition, which I hate it sometimes because I really trust the math, but the main idea is because to estimate mu, sigma, you have to estimate mu, right? If you give you the mu, you can just divide by n. Okay, so that is the only thing. Now, is that okay? Now here is the remaining is the binary data, right? The binary data actually is a special case, so that's why the sample proportion will have a good property to estimate the sample mean. So that is something we don't need to say anything more. The second thing I need to have a remark on here is we call the population variance, okay? And we actually don't adjust n and n minus 1, okay? And the main reason is because this, although it's a bias, okay, this is still a consistent, okay? This is a bias, okay? What we're doing is just we replace this by p, right? And this very naturally we are going to do, but you can easily prove, I mean, using the proof technique we've been proving, turn out this is bias, okay? So it's you need to multiply by adjustment factor, right? Which to make it unbiased. But we look at the textbook, most of them we still use this guy, okay? And there are two reasons for doing this. One is usually when we talk about binary data, the n is very big, right? So n over n minus 1 usually make no difference, okay? So that's why in order to avoid carrying this n over n minus 1, we don't worry about it, The second is it's still consistent, right? So that's not a very big issue there. As I said, n is very big anyway. Okay, so that is not a big issue because when the sample size is big, consistency is more important, right? When the sample size is small, you would focus on the unbiasedness. Okay, but anyway, I mean, we just follow the tradition that have been using. So we just use what the textbook is using. So we're not going to fight the well for this one. Okay. Now we go to interval estimator. Okay. So is that okay before we go to interval estimator? Is there any question? Okay. If no, then we go to interval estimator. So this is the one of the key thing we cover today. And later you will see this interval estimator is closely related to hypothesis testing. We're going to preview later today. Okay, that's a very important thing. So as we have said at the beginning, why we want to look at this is because why we need normality is because we know X bar, okay, is a good estimator for mu. Okay, and the fact that we cannot proceed anymore, okay, without knowing how X bar looks like. Okay, and so that means that we need to invoke either normality assumption. Okay, basically what about this is coming from the Bell. Okay, the underlying population is a Bell, right? So it's basically going back to here just to remind you, is talking about these guys a Bell. Okay, this is the Bell one. This is the Bell. If you have the original one is a Bell, then you will satisfy the normality. Okay, and or if you are looking at a very large sample, okay, so by central limit theorem, this also holds. Okay, so there are two ways to achieve this. Remember, either normality or very large sample, you will lead to this guy. Is that clear? Okay, and and the goal of what we want to do is we want to have a symmetric interval based on X bar, okay, to include mu. Okay, so the main idea is this. Okay, but let me go to the whiteboard, okay, to explain once more what's going on there. Okay, so this is X bar, right? Remember this random variable, right? And this mu, okay. And do note that we never know mu, but so this is a hypothetical idea. So suppose this mu is here, okay. So this is the bell curve, okay. Not fully symmetric, but I think it's okay. So the main idea is the following, okay. And according to the bell, it's like this, right? So you may end up here, you may end up here, you may end up here, you end up here. You don't know where you end up, right? And suppose we have a scenario that you end up here. Okay? This is what you found. Okay. Okay. It can be anywhere in the green one. So, but this is what you found. Okay. It's from the sample. And what you want to do is we want to go left by m, okay, and go left by m, and go right by m, okay. Maybe not symmetric enough, okay. Remember what m by m, okay, and this is called x bar plus m, right? This is x bar minus m, okay. And we have this interval of values, right? And what we are saying is this interval will have high probability include mu. Okay. So just to write that down here is like this, right? Probability that mu, okay, is within, okay. We want this probability, of course, want it to be high, right? So we want it to be high. That means I want this. I will write 1 minus alpha, and I want to write alpha, okay, to be very small. Usually alpha is in the sense of 0.1, 0.05, or 0.01. Okay, so that means that I want to have 90% of chance include the mu, or 95% chance include the mu, or 99% chance include the mu. Right? So with high probability there. Okay, so that is the main goal. Okay, is that clear what we're doing? And now we are trying to show you. Okay, we go with the proof very quickly. So I show you one thing is M turn out to be, okay, Z alpha over 2 sigma over root n. Okay, so this is indeed our central formula. Okay, we want to remind you this will be the goal today. Okay, so we just prove this guy. Okay, and let's go to the proof. Okay, before the break. And before we do that, I talk about some terminology here, right? You look at the slide. Okay, this is what we call ME as a margin of error. Okay, just terminology here, so there's nothing new to learn terminology. So this upper guy, this value is called UCL, upper confidence limit, upper confidence limit. Okay, and they call this guy LCL, lower confidence limit. Okay, and also they would call this whole thing, okay, which is W is 2 times ME, right? It's called the width. Okay, there's nothing but just terminology there. So that is the standard thing. I mean, I don't think I need to talk about this, but before the break, I want to talk about the proof. Okay, the proof will be very trivial. Okay, so don't worry, it's not difficult. Just changing some inequality, which you should know very well when you, I think in the high school you learn that. Okay, the math is very simple. So remember, so don't worry, that will be very simple. Okay, so this is the goal, right? Remember the goal is this guy. Okay, we want our interval will include the mean with high probability. Okay, alpha is very small. Is that clear, this statement? Okay, can you see the statement? Mu is maybe if you have old version, you don't find this one, but this is not some. This is the same as the proof that in the original slide, but they're the same thing. Okay. So now, what we want to check out is, say, suppose you look at this blue thing first. Okay, the blue thing. Okay. In the blue thing is we have mu is less than x bar plus m. Okay, so let's remember how we do inequality is you can subtract both sides by the same number, I mean the same, right? So you can subtract m from both sides. That means that you have this. Okay, so this is exactly what? Exactly here. Can you see that? Okay, so we can do the same for the pink one. Okay, the pink one is here, say x bar minus m is less than mu. What you're going to do is add m to the both sides, right? So basically add m here, right? So maybe I just have this, subtract m, right? Add m to the both sides, right? So you will have x bar is less than mu plus m, okay? Which is, you can see, is the right-hand side. Okay, I hope this is clear how this being done. Okay, is that okay? Now we have continue to look at the purple part, okay, which is X bar is less than mu plus M. What we're going to do is we subtract mu from the both sides, okay? So subtract mu. So that was X bar minus mu less than M. Okay? And we can do the same for the other side. This side is this side, right? Mu minus M is less than X bar. So we can move mu to the other side because it subtract mu, right? So become negative M is less than X minus mu. All right. So that is here. And that is here again. Okay. I guess it's clear what we're doing. Right. And the next step, I think, is trivial to all of you because this is a positive number. Right? It's positive number. So you can divide everything by the same number, the inequality will be the same. All right? Is that clear? What we are doing? Okay? And we just need one last step, okay? Then we're done. Okay, then we'll break. So that is very simple. The very last step is like this. Okay, just to recall this guy, okay? This guy is what? This guy, if we follow normal, right? Right, because we remember the beginning, the assumption, right? X bar follow a normal distribution with mean, mu, sigma square over n, right? So this guy means what? This guy means this is standard normal. Z. Right? So this is Z. Okay? So that actually goes to the, maybe I can go to the next slide because that would be faster. Okay? Is that okay for this one? I'm going to the next slide. Is it okay? So the next slide. So the next slide, as I said, right, because of central limit theorem, we replace it by Z. Okay. So what you see here, remember this is a standard normal, right? So that's why we can talk about a bell curve, right? We can have bell curve here. And Z, right? And remember Z is what? Center is 0, right? And what we want is this is symmetric, right? So it means go to left and the right at the same distance, okay? And it means 1 minus alpha, it means this guy is 1 minus alpha, okay? And because Z is symmetric, right? That means what? That means the following, right? This is just alpha over 2, and this is just alpha over 2. Okay? And if you remember, okay, one more step is, last step is remember, if this is alpha over 2, we write just notation, just alpha Z over 2. This is negative Z alpha over 2. Okay? And now that's done because this guy, okay, supposed to be here, right? And this guy is here, right? So that's why we have this formula, right? Because they should be the same, right? Because this should be the number. And what we learn is learning from your primary school. You just multiply the denominator to the other side, we're done. So that's come the proof, okay? Although, as I said, you never used it anyway, but you understand this formula is coming from the fact that you want your interval would include mu with high probability, okay? And that is the goal, okay? That was the goal. And then I think I convinced you, we have actually proved it. Of course, none of you will be using this proof, but I guess this is good to at least know some of the proof here. I mean, of course, it's not required for your assignment, your test, or whatever, but at least I think this is the only proof we cover in this class. Yeah, I think this only proof only 1 or 2 proof we cover in this class, and we know more proof for that. But at least you feel something, I hope. Okay, so is that okay? Okay, but before we end, let me just this is another proof that I have original, but you just do another way around. But before I end, I guess I want to talk about this a little bit because I found the example would be good, but that would be quick. Sorry, I just take a little bit more time from your break because I think that would be good to do it. Okay, so here I have a sigma equal to 4. Okay, and here I have a sample size of 64. Okay, and it's big enough, so probably okay, we can apply central limit theorem because more than 30, I think it's okay in general. So sample means 3. Okay. So before we proceed, here you can see this will be our good point estimate. Okay. Okay. This is our this will be our good point estimate. Okay. And the thing is, I want to go one step further to have an interval estimate. Okay. So what we're going to do is we're plugging in. Okay. So we want to construct a 95% confidence domain, right? This is, say, 1 minus alpha is 0.95. Okay. So that implies use your high school math. Okay. This is 0.025. Okay. Now, the formula is like this, right? If you remember, plus minus z alpha over 2 sigma over root n. Okay. Then what you're going to do is what you're going to do is try to plug in every number there, right? Because x bar is already here, right? Right? You have x bar is here. Z is already there, but let us go to how to do this, right? This is just the following, right? Let's see again how we do this number here. Here means the tail, the right-hand tail is 0.025, okay? And in Excel, how you work it out is just because you from area to number, so use the norm, it's a bell curve, so norm S dot inwards, okay, and put. But remember, this is only give you the left-hand side, so you need this guy, okay, and this is 975, okay, you put Excel is 0.975, okay, and this will be the answer, so give you 1.96, okay. And I'll do it after I finish this. I'll do Excel. So you can put this number here, okay, and the rest is there. Okay, so you just put in the number. Turn out this margin of error is actually close to 1. Okay, and basically your guess is 3. You just add 1 and subtract 1. That would be your estimate. Is that okay? Maybe to convince you this number is the right, I go to Excel. Hopefully the Excel will work because I think last time it didn't. Okay, so that's good, it worked. So what I left is I'll do this and I'll have a break. So we have a norm as inverse and 0.975. Okay, so that would be 1.96. That is the goal. So that would be how we calculate that guy. Okay, I hope you know how to operationalize this because this is very useful, right? Because this is the correct data. You come with sample mean. Now this class actually go beyond from your high school, right? Because now we know there's one way you can go further, right? It's not just this, it can actually can tell us more. It's interval estimate, right? Come with the bounds, right? And actually, this actually tells you one very useful rule here is when you do the 95% confidence, right? Actually, it's 2 times of the standard error, right? Remember, this guy is called standard error, right? This guy, this is standard error. This is standard error. Here it tells you you'll be 2 times of standard error, right? Because this guy 95 is like 2. Okay, so anyway, so let us have a break and 10 minutes break. Then we will continue our journey. Okay. In the meantime, I'll go around to see if any of you have any question. So I hope that's fine. So I guess we can continue if there's no questions. Okay. So I would like to draw your attention on how to interpret confidence interval. Okay. So just to remind you that, okay, we said confidence interval is we have high probability that the interval will include the mean, right? But the problem is once we have calculated the interval, okay, we cannot use probability. Okay, once we're done, we cannot say probability. Okay, why? Okay, suppose I ask this question. I have a coin in my hand. I toss a coin. Okay, and before I toss it, you will say half is likely head, half likely tail, right? But after I toss it, I close it. Okay, then it's either head or tail. Okay, and your guess is either right or wrong, right? So that means that once I calculated, I have interval, it's either in or not in. Okay, there's no probability. Okay, there's probability before you do it. Okay, there's no probability after you're done. So that's why we don't call it probability interval. We call confidence interval. Okay, and how can we interpret the confidence? The confidence idea is actually followed from the idea of what we call long-run experiment, long frequencies. Like suppose we do many samples. Every time we construct the interval, and say you construct hundreds of this interval, right? And what we say we have 95% confidence is like out of this 100 interval, 95 of them will include the population mean mu, but we don't know which one. Okay, we just know 95 of them will include. Okay, so that is the main idea. Just if you want to look at this graph, it's like, okay, we do the sample, right? Then you will end up in maybe one of these number, right? Depend on the sample you got, and we construct the interval, and 95 of those will include mu, but we don't really know which one will include. Okay, so if you ask me, I have an interval, ask me which number is the best guess, I don't really know, right? Maybe besides the sample mean, I don't really know which one is more appropriate. Okay, which one is more likely to be there or not. So that's the interpretation. I hope that I can convince you why we call confidence, not probability, is because once you're done, there's no probability. Okay, it's either whether you're in or not in. Okay, the probability is describing the process you do. It's a random variable. Okay, the interval you calculate is already estimate. It's not an estimator. The estimator you can talk about probability. The estimate you cannot. You cannot. Okay, so that's why you have to carefully distinguish what's estimate or estimate. I hope that's clear. But this is rather a philosophical idea. But at least you know there is some tricky thing there. And if you learn statistics, probably you pick up if you interpret it wrong. Anyway, if I have multiple choice, this will be one of the questions. But luckily, we don't have multiple choice in our class, so that would be that we don't ask this kind of tricky question. So the next is actually it's not that difficult. The idea is very simple. Is unknown variance. Okay. And the example we have done, we assume we know the sigma square. Okay. And in general, we don't know sigma square. Okay. Of course, although we don't mention, if you look at the book, they will tell you there's a certain way to estimate sigma square, even though we don't have a good estimate on that. Okay, there's some way to do it. One of the way you can imagine in your head how to estimate sigma square from historical data is you know what kind of value can be. Okay, you can calculate the range. Okay, how to estimate sigma square. One of the way to do it in the real world application, if you really want, is look at the range of the data, the max minus mean, right? If you recall what we learned in the, okay? And max minus mean is the range, right? The small minus. And this one give us, can tell us how to have a upper bound for the sigma square, right? Because sigma square is looking at each data different from the mean and square, right? Range is the maximum difference, right? So if you square the range, that will be the upper bound, right? The variance cannot be more than the range square, right? Of course, you can learn some inequality and tells you you can reduce the size of range to guess upper bound of the sigma square, right? Because you know, for some data, you pretty much know the range, right? Suppose look at income, right, of your customer, probably might be okay to say set the range, say from 10,000 to 1 million, right? And that, or if you want to guess Hansen index, right? What's the maximum minimum? Usually you have some idea, right? Say in the current state of the world, right? You don't expect the Hansen index to go beyond 20,000, right? For today, right? It cannot go below 10,000 for today, right? Maybe something will happen, but we assume that will be appropriate. In that case, the sigma can be really, we can guess, okay? But anyway, that is actually the use of range, but we didn't mention in the beginning, but that would be actually range can be useful to estimate. But anyway, let us consider S, okay? And if you don't only know S, how can we proceed, right? So that is coming from the idea we learned in the previous chapter, which essentially said, if we replace sigma to S, okay? Before this is sigma, right? Because remember the formula we learned by normality is this guy, right? And sorry, this is just Z, or we call normal CO1, the bell curve, the Z bell curve, right? And replace S will be the T bell, right? So just to remind you what looks like the T bell and the Z bell, right? It's like this, right? If you have the Z bell, it will look like this. Okay, this is 0, this is Z bell. But when you have the T bell, okay, Tn minus 1, okay, it will look like this. Okay. And this T bell is lower the height, taller at the ends, okay? It's still symmetric one, but has a higher kurtosis, it's higher tail, okay? And remember, when n is very big, they're the same. N big, T will be very close to Z, okay? Because when n get bigger, the tail will become smaller, the peak become taller, okay? So, and you can see, we can follow the same proof. We are not going to do it, but we actually can show, basically you just replace this, right, from sigma, right? And this guy just come from here, okay? And then you're done, okay? So basically replace it. So what do we learn from this is just the formula, because the same proof would apply, which I guess none of you would be interested in. We working the proof is this formula. So this is the thing that you need to remember. I mean, of course, probably you want to copy it to your bring to the exam venue will be this formula, right? It just the same format, right? Just to remind you, this is the format we have learned for when you know it, right? So that's basically the main changes is just this guy and this guy, right? Of course, this is alpha over 2 here, right? Just change the T and minus 1 alpha over 2. Okay. So I guess it's good to go through the example because this example is actually what you were doing. Okay, so to go for example, then you will hopefully you will be happy. Okay, so this is the example that actually you will be using. Okay, and in your application or in your analysis. Okay, so we have a normality assumption here. Okay, And random sample with sample size n is equal to 20. Sample mean is 3. Sample standard deviation is 12. Okay? So construct a 95% confidence level, right? So that is x bar plus minus Tn minus 1 alpha over 2 s over root n. So this is the formula. Okay. And by construction, s is here, right? S is here. Right. So this is done. Okay. And the color, right? 3 is here, okay. And let me design the color. Green, yeah, green. Green is here, and green is here. Okay. So what is left is the middle guy, right? The middle guy. But the idea is saying we need to construct the 95% confidence, right? 1 minus alpha is 0.95. So alpha is 0.05, okay? And then alpha over 2 is 0.025, okay? So the idea is the following. Let's see it, okay? So this is 0. We want this area is 95%, 0.95, okay? And because of symmetry, okay, these two, okay, should be add up to 5%. And because they're same, they're by 2, so it's 0.025. 0.025, okay? And what you can do is learn the thing you learned in the kindergarten, add up these two, okay? 0.025 and 0.95 is 0.975, okay? So because this is the t of n minus 1, it's t19, okay? So what is this value? Will be just t dot inverse 0.975, 19, okay? So that is what you get. You get this number, okay? So this is what you get. So I can show it Excel, but this is the idea. Then you plug in everything, and this margin error is large. It's like 5.6. Okay. So you would be adding and subtracting 5.6. Okay. Is that okay? Now I want to show you the Excel, right? So because I want the this guy equal to t dot inverse 0.975, 19. Okay, so that's how you get this number. Is that okay? Okay, so that would be the. Is that okay? Is that okay? Okay. Is there a question? If no, then we go to the next one. Okay. So that's a goal because you would be this to a guess. Okay. Now the other one, this is also very straightforward. This is another formula when you apply to binary data. Okay. And you can see this is exactly this formula. Okay. This is this guy. Okay. And what actually we are doing is because this guy is we estimate by this. Okay. So that's why you take a square root. Okay, so that's how you come with this one. Okay, and x bar is p. Okay, so everything the same formula. Okay, and only thing you need to worry is only this equation. They must be at least 5 for this to be a good approximation. Okay, so basically what we're trying to show you is just another formula when you calculate the proportion, right? And this is interval, right? Because okay, is that a question? Just sorry, it's another formula, but because this is very straightforward, right? Because everything is the same, but just because we have binary data. Okay, so to demonstrate, I think it's good to look at the example again. Okay, so I have a sample of size n. Okay, and I have p is 0.3. Okay, so this is our point estimate. Okay? Point estimate. So what we need now is I want to have a 95% confidence. Okay, so 1 minus alpha is 0.95. Okay, so remember alpha is 0.05 and alpha over 2 is 0.025. Okay, so the interval, remember the formula is p plus minus z alpha over 2, p 1 minus p over n, take the whole square root. So this is the formula. Okay, and just plug in the number. Okay, this is what we have covered, right? So this is covered already. Okay, and the rest will be just put in the number here. P is 0.3. This is p, right? This is n. Then turn out to be this margin error is 0.1122. Okay, so you just add and subtract this number. That's what you want to get. Is that clear? Is that okay? Okay, so there's nothing but just plug in the numbers. And because the same idea, right? The special case, so that's why nothing to explain in this context. So basically just the same, you can see the same formula, just keep applying. And although it looks simple, actually it's very useful. Because it's actually you collect data and you do an estimate, and this is what you're doing. Is that clear? Okay. So is there a question? I guess before we proceed, I think I want to mention one thing which I forgot to do is look at the T table. Okay, the T table. Okay, and what I'm going to do is like to go to the web and look for the T table and try to show you that how I can do that. You can do it because you either you could Excel or you can print it out. So what I do is I just pick up the dummies table. I just do T table. I just check out this guy, and maybe I open this in the new page. Okay, and of course you can construct this easily. Okay, and remember I have the tail here is I have this guy. Okay, 25. Oh, can't see. So this is the 0.025 because the tail. Okay, and remember the question we have is the T here is like 20.025, right? Degree of freedom is 19. So look at this graph here. DF, right? Degree of freedom at 19, just go down to 19. So this is number 2.93. Okay, so that's how you're going to get this number if you use a table. Okay, so but you can see this number actually not too much different from 2, right? So actually the Z is, I mean, in some cases like people use rule of thumb is like 2, right? Because when you go up, look at this graph thing, go up, right? When 1 or 2 is a little bit different from 2, but when you go further than say more than 10, say beyond 10, right? It's like very close to 2 already, right? Because and you go further, right? At the end get to 1.96, right? So that's why what I said, right? When you have many samples, then actually go to 2. And in this table only give you up to 30. Okay? So that is exactly what you say the central limit frame apply when you more than 35. Right? Because that is very close already. Is that okay? Okay. So if there's no problem, then I guess we go to the very last part of our class. It's called sample size. Don't worry. I guess you are tired after almost a 1 hour lecture. These are exactly the same what we cover, right? Remember the leading cases we have x bar plus minus z alpha over 2 sigma over root n, right? The main idea is this, right? Because it's very often before we do our estimation, we actually want to fix this guy, margin of error, right? Because margin of error is how precise our estimate, right? Because I want to estimate our, say, income or spending up to a difference of 100, right? How precise we want, right? We want to precise up to 1,000, up to 10, up to 1 decimal places, right? Up to how many you want, right? So this is the margin of error, is how accurate you want, okay? And here you can see this guy is independent of our sample, right? And this guy also independent of our sample, right? Because we would be doing, this is, we know, right? So that's the only thing you can see. N and ME are inversely related, right? The higher the ME, the lower the N, or the lower the ME, you higher the N, right? So let's write down ME, okay? It's just over 2 sigma over root n, okay? And what we want to do is like the high school algebra. We want to write what's n to the what? Okay? How to do this high school algebra? You have to first put root n be the subject, right? You move that to the other side and move m to the other side. So that's what you get. Sigma over me. Okay? And because n is a positive number, right? Everything positive, right? So that means that you can square both sides. All right, take square. Okay? So that means that you have sigma of over 2 square, sigma square, me square. Okay? So if you have some desired accuracy or precision, right? Just plug in a number, then you know how many samples you're gonna get. Okay? So let's get started. That's the main idea of this, or the rest of the slides. Okay? So that is nothing but just we have done already. Okay? So just this is like this, right? So we have this is our formula, right? And again, you ask how can we know sigma square? As I'm already hinted, that come from the range and come from some other previous prior tests, right? Because you can estimate this because historically you can come up with S square, right? That can come from previous S square and come from the ideal range and so on and so forth, right? And there's no problem to overestimate sigma square here, right? Because that makes your margin of error larger and that makes your n get bigger, okay? There's no harm of overestimate, okay? And it's always you can get upper bound, so it's no problem. There's no problem. You don't need a precise estimate for sigma square, okay? And and you just make it the subject, so that's the formula you get. And notice here I have a run up, right? Run up function here, which means that if this guy is 11 points, I suppose I have my number is like 18.5, okay? That's given us 19. If it's 17.1, it's still, it gives you 18. If only 16.0, okay, they will give you 16, okay? Always add 1 unless the last everything behind is 0, right? That's the biggest integer, Okay, the smallest integer that is bigger than the number, right? This one, there's the rounding up. Okay. So you see example why I round up, because this is a mini, because 18.5 do the job, but you cannot do 18.5, so you need 19. So that's the idea, right? So the minimum sample we need. So see the example. So don't worry, just plug in the numbers. Okay. So here we have the idea is very simple. We have sigma equal to 10. Okay, that's what they said. I want alpha, right? 1 minus alpha is 0.95. I guess now you would see alpha over 2 is 0.025 without drawing. Okay, and now we have one. The sample, actually the margin of error is 4. Margin of error is 4. Okay, so from what we have learned, this is 1.96. There's no problem. Okay, and margin of error is 4. We have done it, right? And just plug in the number, right? Just because this is a formula is like this, right? Square, sigma square, AME square. Okay, just plug in all the number. Turn out to be 24.01. Okay, so that's why you need 25 sample to achieve the accuracy plus minus 4. Okay, so that's nothing new, but just plug in the number there. Okay, is that clear what we are doing? Okay, this is the one step before it. Is before we do the sampling, if we want to achieve the margin of error is 4, we need to have 25 samples. Okay, is that clear what we are doing? Because I hope, because this is where you actually do the survey for your group project or individual project, that is how you design your sample size, right? And at what time you should stop, right? This is the way, right? Is that okay? If no question, we go to the very last one. Okay, very last one. Okay, this is the same thing here, but do note that sigma for proportion data, sigma square is pi times 1 minus pi, right? So that's why sigma, this is sigma, right? This sigma square, right? The formula, right? So just plug in there. So the only difference is just like we have give you pi, if you know the pi, just the same formula, nothing new. That's exactly the same formula. Okay, is that okay? The same formula there. Okay, so let's see the application. I guess it's so straightforward. I just tell you what it's doing here, right? So here the question is, this is our pi population proportion. This is 1 minus alpha is 0.95. Okay, again, I'm not going to. It should be clear to you. This is 0.025, and margin of error ME is 1.96. Okay, so and first thing we calculate is pi times 1 minus pi, right? We know 0.4, 1 minus 0.4. Okay, and give you 0.024, right? And this we know very well. Okay, just to write down again what's this, how to calculate this, guys. Norm S inward 0.975. Why? Because 0.5, 0.95, 0.025 on the both sides, add up, it's 0.975. Okay, and margin of error is 0.01, so just plug in all the number here. Okay, do note that you don't square. Okay, there's no square here, and you get 92.19 is 93. Okay, so that is the thing. Is that clear? Because it's plug in, I'm not going to spend too much time on this. It's just plug in the numbers. Okay, and the logic already there. Okay, is that okay? I mean, because going through this is like an insult to your intelligence, right? I mean, plug in the number. I mean, I guess I need not talk too much. Okay, so I guess I spent the last 4 minutes to talk about this thing. Okay, proportion has a luxury of things getting simple. Okay, so actually the good thing is here we require us to know what is 0.4, right? Which is something actually is difficult to know unless you have data that actually have been relatively constant, right? But in the case that for proportion, actually, we can use the most conservative thing. We use 0.5, okay? We use half. Why? Look at the graph here, okay? I think it's good to look at this graph. It's very simple, okay? The graph tells us pi times 1 minus pi, right? When pi is 0, this is 0, right? When pi is 1, this is 1. And this is a contrasted function, right? Pi square plus pi, right? Contrasted. So it's like this graph, right? Like this one, right? And the maximum achieved is when it's 1/2, this is 1/4, right? So we don't know where, so we can use the most conservative case. This is this, okay? And this will tell us the best thing we want to do, right? Of course, in reality, when you calculate, right, you get the P, right? You calculate will be just P times this guy, right? But when you calculate pi, we'll use 1/2, but that doesn't matter. You are more conservative, right? So at the end, actually, it's more narrower. Doesn't matter, right? Because you are going to get things more accurate, but the choice of n we're doing here is going to the minimum required. So you would do more than you need to, because unless your P is actually 1/2, right? Then you actually overdone, but that's okay. We should be more conservative than more aggressive. Is that clear what we're doing? Right? Because at the end of the day, you will be doing this, right? This is your calculation, right? Based on 1/2, right? Based on 1/2. But this is actually how you actually do the calculation, right? We use a larger one, doesn't matter. When you do the calculated n, at the end it's smaller. Is that clear? There's no problem making it smaller. So let me quickly to check again what's going on, right? The only difference is here, just highlight. The only difference is I use this guy, 1/2 times 1/2, okay? So that means this guy is just 0.025. So that's the only difference, everything the same, okay? So actually you can see the difference is before I think I have 91, right? Now I have 97, okay? Not too much different, but that is more conservative. Okay, and this is usually you want to do. And just one final remark, I guess many of you want to go home. Is this explain why when we do political pool, right? Ask whether you elect to whom. No matter you look at the UK, look at the US, look at everywhere in the world, they always look at 1,000 or to 2,000, right? Actually, you can see this almost within 1% or 2% error will give you these numbers, right? So that's why when you do proportion, it doesn't really matter how big the population is, right? When you have margin of error, then you automatically give you the size of the pool when you ask people to elect whom or who. Okay, I guess I overrun. No, it's okay. I just had the right time to stop. So I will see you next week. Remember, your homework is due on Friday. Okay, just make sure you do it. Okay. Have a nice day. I will see you next week.